What you should know about water, solutions, and pH. In the video about atoms and molecules, it was discussed that water is a polar molecule that forms interactions with other water molecules called hydrogen bonds. It was also mentioned that salts dissolve easily in water. Now I'm going to talk about more properties of water and what will or will not dissolve in it. Any molecule that easily dissolves in water is called hydrophilic or water loving, from the Greek words hydra for water and philia for love. Ions and polar molecules are both examples of this. Molecules that do not dissolve in water are hydrophobic, again using the Greek word for water combined with the word phobia for fear. Lipids like fats and oils are defined by the very fact that they don't dissolve in water. When a polar or charged molecule dissolves in water, the water surrounds the molecule with the opposite charges pointing towards each other like magnets. In the case of a salt, the negatively charged oxygen end of the water points towards the cation, and the positively charged hydrogen end of the water points towards the anion. Sugars, like glucose, also dissolve in water, but sugars don't dissociate because the atoms are covalently bonded. However, sugar molecules are full of polar bonds, which make lots of places where water can form hydrogen bonds with parts of the sugar molecule. All polar molecules interact with water in a similar way. When a molecule can mix easily into a liquid, that liquid is called the solvent. The molecule that mixes in is called the solute, and the two combined are the solution. Water is the most common solvent in our bodies. Salt water is an example of a solution because sodium and chloride are both happy to mix in with water. You likely know from experience that if you let a mix of oil and water sit for a while, the oil will float on top of the water. When you shake up the mixture, oil droplets form, but if you let the mix sit still again, the oil will eventually all come together and once again float on top. This happens because oil molecules are hydrophobic. When you shake up your mixture, the water surrounds the oil droplets in a cage. These cages are highly ordered, which means they take a lot of energy to maintain. When the small cages move around and merge with other cages, fewer water molecules can be involved to surround the same number of oil molecules. The fewer waters in the cage, the less energy involved. In the case of our oil water mix, the cages will keep merging until eventually the oil completely separates. This principle is called hydrophobic exclusion. Large molecules may have some regions that are hydrophobic and some regions that are hydrophilic. Molecules that have both hydrophobic and hydrophilic regions are called amphipathic. Think of amphibians. They live in both water and air at different parts of their life cycles. The word pathic is from the Greek pathos for experience. So amphipathic molecules have both experiences of being hydrophobic and hydrophilic, depending on which part of the molecule you are looking at. Soap molecules like sodium laurite are examples of amphipathic molecules. If you add soap to an oil water mixture, the soap surrounds the oil molecules with its nonpolar part, but its polar part is happy to be in contact with the water. In this way, the soap can keep the oil molecules from coming back together and keep them dissolved in the water. Once all the oil particles are surrounded by soap molecules, they easily wash away. Remember that polar covalent bonds involve an imbalance of electrons, where one atom pulls on the electrons a lot harder than the other. Since hydrogen atoms contain one proton in their nucleus, their pull on electrons is about as weak as it gets. And even in covalently bonded molecules, they sometimes give up those electrons to the side with a stronger pull. Oxygen has a very strong pull on electrons, so, in some water molecules, oxygen will tug so much more strongly on the electrons that it will become two ions, a hydroxyl ion and a hydrogen ion. Most of the water remains together. In pure water, the concentration of hydrogen ions in solution is 10 to the negative seventh molar. To put that in perspective, that's 500 million times less than the number of water molecules, but changing that number just a bit can make a big difference in how a solution behaves. A few things about terminology. Because hydrogen atoms contain one proton and no neutrons in their nuclei, when they lose their one electron, all that is left is a proton. Therefore, a hydrogen cation and a proton are actually the same thing, and you'll hear those terms used interchangeably. Also, protons don't actually exist free in an aqueous solution, but rather often latch on to another water to form hydronium ions. Depending on the textbook, you'll see these components represented or referred to in any of these ways as hydrogen cation, or often just hydrogen ion, proton, or hydronium ion. Remember that water has 10 to the negative seventh molar hydrogen ions in solution. If we look at this and we see the exponent of negative 7, 7 is actually the number of pH for water. A pH of 7 is defined as being neutral, neither acidic nor basic. When acids dissolve in water, they generate even more hydrogen or hydronium ions than water alone. Like water, hydrochloric acid has a polar covalent bond, this time between the hydrogen and chloride. But when it dissolves in water, HCl completely separates into ions. A solution of hydrochloric acid therefore has a lot more hydrogen ions in solution than water does. In a zero point 0.1 molar solution of HCl, there are zero point 0.1 molar hydrogen ions. Saying zero point 0.1 is the same as saying 10 to the negative 1. So we know that zero point 0.1 molar HCl has a pH of 1. Bases do the opposite of acids. They take the hydrogen ions out of solution. Sodium hydroxide, also known as lye, has an ionic bond between sodium and the hydroxyl ion. In solution, sodium hydroxide completely dissociates into these ions. The hydroxyl ions react with any free protons, making water molecules. In this way, the number of hydrogen ions in solution decreases. However, the equation for figuring out pH from molarity isn't quite as simple for bases. That's because when you have a zero point 0.1 molar sodium hydroxide solution, you know it generates zero point 0.1 molar hydroxyl ions, which gives you a pOH equal to 1. To figure out pH, you have to also know that pOH plus pH equals 14. So you can figure out pH by simply subtracting the pOH from 14, equal to 13 for a zero point 0.1 molar sodium hydroxide solution. So acids generate hydrogen ions, and bases take them out of solution. When you mix together equal concentrations of a strong acid, like hydrochloric acid, and a strong base, like sodium hydroxide, the ions that each compound generates recombine, and you end up with water and salt. In this specific example, the salt sodium chloride. The concentrations of free hydrogen ions in the solution is now about the same as pure water. This process is called neutralization because the pH came close to a pH of 7. Ammonia is also a base, but it works in a slightly different way. Ammonia molecules have a nitrogen bonded to 3 hydrogens. The nitrogen atom has 2 electrons. It doesn't have to share with anything else to have a full outer shell. But those electrons are attached to hydrogen cations in solution, and therefore bind with them to form ammonium ions. Since ammonia steals the hydrogen ions out of the solution, it too is considered a base. Weak acids and weak bases are defined by the fact that they don't cause big changes in hydrogen ion concentration. When you put ammonia in water, it pulls some hydrogen ions out of solution to form ammonium ions, but most of the ammonia just sticks around as itself. This makes it a weak base because it doesn't cause a big change. When you add a salt of ammonium ions, like ammonium chloride, to the mix, you can shift the balance so you end up with an equal amount of ammonia and ammonium ions in solution. In this mix, something interesting happens. Let's take the chloride out of here and simply simplify this view back to just thinking about ammonia and ammonium ions. You can see here that ammonia is base because it takes the hydrogen ions out of solution. If we flip the equation around and think about it from the other direction, you can see that the ammonium ion is actually an acid because when it falls apart, it adds hydrogen ions to the solution. Because ammonium ions and ammonia molecules have the same atoms with the exception of having or not having that extra hydrogen, they are called a conjugate acid and a conjugate base, a matched pair. A mix of conjugate acid base pair is called a buffer because it buffers against changes in pH when other compounds are added. Let's take a look at how that works. If you add a base to a solution, like sodium hydroxide, it wants to pull hydrogen ions out of the solution. But when you mix it into our ammonium chloride buffer, more of these can be generated by ammonium ions dissociating. In that way, the number of hydrogen ions in solution stays roughly the same even after adding a base. If you add an acid like hydrochloric acid to this mix, it will try to generate more hydrogen ions. But then the ammonia present in the solution can pick them up and make ammonium ions. Thanks to the equilibrium between the molecules in the buffer, as long as you don't add too much of either an acid or a base, the buffer stays pretty darn close to whatever pH you started with. Buffers have essential roles in human health. In your blood, the balance of bicarbonate and carbonic acid helps keep things around a pH of 7.4. In your urine, phosphate buffers help keep things to an average pH of 6. Note that these are different pHs, and neither one is perfectly neutral. It's important to remember that buffers can be any pH to start, but what they have in common is that they keep the pH as close to that starting value as possible. See you next time.